Hello, my name is David Andrews. I'm from the University of East Anglia in Norwich in the UK. I lead a research group there. We work on the theory of quantum electrodynamics. One of our main interests is in the theory of optical orbital angular momentum, which is a fairly recently discovered attribute of light, where some people describe it as a light with a twisted beam or optical vortex structure. And we're particularly interested in means of generating those things directly from molecular arrays. Mostly that kind of light is produced by passing other beams through optical elements, but we think we can do that more directly with our new scheme. So let me try to explain what an optical vortex is like. In regular beams of light, independent of the polarization, which can do all sorts of things, plane polarized or circularly polarized, but the photons travel in laser beams usually in pretty much a straight line. In these optical vortex beams, they kind of wave around in a helical form around the axis along which the beam propagates. And so there's a new kind of angular momentum associated with that, and that's where lots of the interesting things come into play. The challenges in this area are really, many of them are quite fundamental theoretical ones, because one of my colleagues has referred to the advances in this area as necessitating a complete rewrite of all the books of optics. So the extent of reconsideration of theory is that extensive. So we're working in that area and trying to provide a basis for future applications. So the applications cover a variety of different areas. They range from simple rotational activation of microparticles. You can get the little particles to rotate around the beam, for example. That's been proven quite a long time ago. But because the photons in these beams behave differently, it's now believed it's possible to encode more information in those things, and that has quantum information and communication potential. We've also done some work on a process called optical binding, which some people regard as a means to achieve optical assembly of particles. This is where particles which are held in an optical trap actually experience a light-induced force that pulls them together, but holds them at a non-contact distance. And so when you have a large number of particles, or a reasonable number of such particles in a small volume, it may be possible to engineer through the laser beams which impinge on the structures a means to assemble them into predetermined forms. Yeah, coming from a chemistry background, I tend to think in molecular terms, and it's interesting because some of the new advances actually have now reached the point where molecular implementation of some of these principles has become possible where in the past it really wasn't. But also many of the principles that apply to molecules also apply to things like quantum dots and so on. So it's a different kind of area of the nanoscience field. So in the UK, as in the US and many other places in the world, there are considerable pressures now on securing funding for research. I'm in a fortunate position of having quite good funding at the moment, but many of my colleagues are finding it very, very difficult. There's an increased focus on end applications, which makes life at the fundamental end of things more complicated than it used to be, and everything is just very much more competitive. So for me, at my stage in the career, I just feel particularly sorry for those who are just starting their careers, because it's so much more difficult for those people than it was when I started my own. So in an applications-oriented part of science and technology, one has perhaps a clearer vision of where the research ought to be headed. At the fundamental end, it's different, and part of the challenge is really to conceive of new processes, new ideas, new materials, which might produce something that is of ultimate interest, but it's very hard to see what the end applications might be, and there's so many examples of science of how that works. So generally speaking, it's very hard to look very far ahead in science and to see what the outcome of the research at the fundamental end, at least, is going to be. And there are numerous examples of how really major transformational technologies have emerged from things that were never envisaged. The internet is one striking example, but there are many others of how research in a particular area had just totally unforeseen spin-offs. So it really underscores the need to fund that fundamental research